These are the notes on density, which is a very important concept in science. We already went over the definition of chemistry. Chemistry is the study of matter and how it behaves and interacts. Baskin-Robbins has 31 flavors. Heinz has 57. Matter has 118 flavors, the elements on the periodic table, which we're going to be studying. The periodic table, of course, are the 118 different flavors I was talking about, and we will be studying these. You could sort of say this is the focus of chemistry. These are the different flavors of matter other than the subatomic variety. We'll get back to this a lot. So I told you that chemistry is the study of matter, but I never actually gave you a definition of the word matter. What is matter? And so now I'm going to do that. It turns out matter is anything that has mass and volume. So if you have mass, and we'll discuss what that is, and volume, then you're matter. Now, it is pretty hard to have one without the other. It's pretty hard to have mass without volume or volume without mass. If you had mass without volume, that would be what we call a singularity, and that has been theoretically proposed but never actually observed. So chemistry is the study of matter. It's pretty important to know what matter is, and matter is what we are going to be examining next. So matter is anything that has mass and volume. We just said that. So what's volume? First of all, volume is the easy one. Volume is the space an object occupies. It's how much room it takes up. Think of a box, right? The box is occupying a certain volume up to the edges of the box. Think of a ball. The ball is occupying the volume right up to the edges of the ball. It's the space it occupies. That's a very simple concept. Mass, on the other hand, is a little bit harder to define, at least especially in words, because you can say that mass is the quantity of matter in an object, but that's kind of funny because look at how we defined matter. Matter is anything that has mass and volume. And then we're defining mass using the word matter. We're defining the word matter using the word mass. It's kind of going in a circle there. So in order to jump in on that circle to begin to understand the concept, well, you have to measure mass. And you will be measuring mass in our labs. And for the time being, because we're doing the video labs, you will see my children measuring mass in the videos, so you'll get a sense of what it means. That's the best way to get a sense of what the word mass means. And what do we measure mass with? We measure it with a device called a balance. So you will see a lot of this in our lab this week. And measuring mass is a very, very important thing about matter. It's one of the things that we can put a number on. Very important. Now, weight, on the other hand, is very different. Now, a lot of people think weight and mass, they seem to be the same thing. So what's the difference? Well, mass is something that is intrinsic to the amount of matter you have. Weight depends on how much matter you have and how much force is acting on it. So weight is kind of wishy-washy. We try to avoid using it in chemistry. We use it quite a lot in physics, though, because physics deals more with forces, so we have to understand weight. So in chemistry, we're going to avoid talking about weight, just so you realize it is different. Try to talk about measuring the mass of something, not its weight. You put it on a balance, just like you stand on a scale to measure your weight, right? But mass is a much, much, much more important thing to know about an object than its weight. Your weight is very wishy-washy. You might not realize this, but your weight is not always the same. And not just because you went on a diet or you ate a lot or something like that or exercised a lot. Your weight changes depending on your motion. So in an elevator that it starts moving upward or starts moving downward, your weight is actually different. And your weight would be different in different positions on the surface of the Earth. And of course, if you were on the moon or Mars, completely different. So weight is very, very wishy-washy, variable. Mass is solid. So we like to use mass in chemistry. Okay. This brings us to our next major concept, which is density. The density of an object is the mass of that object divided by the volume of that object. So since all matter has mass and volume, therefore all matter must have density. So densities are expressed in derived units, such as grams per cubic centimeter, that's what that one is, or grams per milliliter. I'll talk about this in a moment. What a derived unit is, that means density didn't get its own unit given to it, like just densons or something. So density is given by the equation D equals m over v, or density equals mass divided by volume. So you can't go out and directly measure density. There's no such thing as a densometer that just measures density, ka-ching. What you need to do is go measure the mass and go measure the volume, and then when you divide them, you can calculate the density. The density of an object is usually very characteristic of what it is made of. If you want to know if something is made of gold, check its density and you'll find out. If you want to know if something is made of iron, check its density. That should tell you. Density is very characteristic for most materials. So density is the ratio of mass to, what does the V stand for? Volume. So you've got to know what mass means. You've got to know what volume means. You have to know how to measure them. And we're going to be doing some exercises with this, including our first lab. We will be doing these calculations. And then you take the mass divided by the volume, and you wind up with your density. So D equals m over v. This is an equation that you should definitely memorize. You're going to know it after using it many, many times. So make sure to learn this equation. Let me show you an example of a density calculation. So density equals mass divided by volume. Mass is often measured on balances. So you can have electronic balances, or you can have triple beam balances, or you can have your traditional two-pan balance, one versus the other. That's the very old-fashioned kind of like Libra balance, like in the zodiac, like the Libra symbol, or the symbol of justice, the balances of justice. Volume, on the other hand, well, sometimes you can measure it just pouring a liquid into a container. That's the easy way to measure volume. And sometimes it's not quite that easy. Sometimes you have to actually measure and use geometry. But if you do get a mass, let's say 300 grams, and you do get a volume, let's say 150 milliliters, well, then you can calculate the density just by dividing. Well, clearly 300 divided by 150 gives us 2. But the question is, what happens with those units? You've got grams on the top, milliliters on the bottom. Those don't really divide into each other. So what you wind up with is a combined unit, a derived unit that looks like this. Grams per milliliter. Notice that slash is overhanging the milliliter, meaning that milliliters is in the denominator. What this unit really means is it's 2 grams every 1 milliliter. That's what that means. We just don't show the 1. Okay, so in every milliliter, you've got 2 grams. That is the density of an object. But a milliliter, if you remember from the notes on the metric system, was actually just a little tiny cube that is 1 centimeter on each side. So there's another name for a milliliter. It's actually called a cubic centimeter. cm to the 3rd power is called cubic centimeter. In medicine, they write that cc for cubic centimeter. So 2 grams per cubic centimeter is actually the identical density as 2 grams per milliliter. So you've got to start recognizing those 2 different density units that we usually get. Now, by the way, generally we see this one, grams per cubic centimeter, when we have a solid object. And generally we have the grams per milliliter when we have a liquid material. That's usually what you see, but actually they mean the same thing and they're interchangeable. When your object is a solid, obviously you can't just pour it into a container to read its volume. I have a little milliliter shown in the upper left corner there. That red cube is a milliliter. But remember, again, from the notes on the metric system, that a milliliter is actually a little cube that is 1 centimeter on this side, 1 centimeter on that side, and 1 centimeter on the other side in all three dimensions. A cube, of course, has the same length in every direction. Interesting. So there is a way to figure out how many milliliters fit inside an object by measuring the centimeters on the outside. So consider this box at the bottom. I'm going to fill it up with milliliters. Let me just get started. Well, I can fit one right there. Oh, it looks like I can fit more across. I can just keep putting them across. Oh, they fit in nicely there. But I can fit another stack above that. And obviously that does not fill up the entire volume of the object. So I'm going to put in another row. And one on top of that. So notice what I'm doing. I'm filling up a volume with milliliters. Well, we can't really do this, but you could imagine this is what we're doing when we measure. Let me put in another row. Oh, good. That gets us right to the front. And then one more. So notice what we've done there. We've just filled up a volume with those little milliliter cubes. Now, they don't always fit in so perfectly, so an exact number of them, but in this example, they do. So what's the easiest way to get the volume of a rectangular block, a rectangular object or prism? Well, my favorite trick is always pick one corner. Like, let's say this one. If you pick one corner, you can be certain that all three dimensions are meeting at that corner. So then from that little corner that I've selected, let's measure going across to the left. Now you could call that the length, okay? It really doesn't matter which one is which. Of course, it's width times length times height. It doesn't matter which order you say them or which one is which. Depends on which way you hold the object. So let's just say that one is 5 centimeters. And then if I were to multiply that times the other dimension, let's say the dimension going backward from there, which is 3 centimeters, well, obviously if I were to multiply those together, I would get 15 square centimeters squared. That would actually be an area, not a volume. So I need to multiply by the third dimension, which in this case is going down from that corner. And of course, it's 2 centimeters. So notice if I were to multiply the 5 times 3, I get 15 square centimeters, times 2, what do I get? 30 cubic centimeters. So the volume of this rectangular block, after multiplying, doing a little bit of geometry, is 30 cubic centimeters. And that's the way that we find the volume of solid geometric objects. This works really well when an object is a nice cube, or if it's any sort of geometric shape, like a cone or a cylinder, okay, or a triangular prism. And this is how we do it. We're going to be doing this in our first lab. So when it comes down to it, the concept of density is actually fairly simple. We have an intuitive sense of density. Just think about it. When you go to pick something up, you sort of expect it to have a certain mass. You're expecting something. So if something has less mass than what you expected, well, that would make it low density, like the inflated blue ball in this picture. That means it doesn't have as much mass in that volume as you might have expected. Or if you go to pick up that shot put, which is a solid ball of iron there on the right, it's going to have a much greater mass than what you expected for an object of that size. So for that volume, it has a whole lot of mass in there. So what does density mean? It's how much mass is packed into the volume. In each milliliter, how many grams are there? If you were to cut those up into little milliliter cubes, how many grams would each one be? How many grams would there be in each little cube? So that's what density means. And also, obviously, looking at these two balls, imagine which one would float. If you threw those into a pool, let's say a swimming pool, which one of those is going to float? You know, okay? The one with the low density. In fact, in order for something to float, its density must be less than water. If something is denser than water, it sinks. If it is rarer than water, which is the opposite of dense, that's the word we use, not necessarily something that's hard to find, like a rare coin, it's just less dense, then it's going to float. After we do some practice calculations, we are going to do the density lab. This will be our first lab, and we're going to do it based on a video this time. So I had my children perform the experiments. They did their best. And of course, everybody makes little errors, so pay attention to that. And you can sort of see what it's like to take measurements. I find that when I do it, I know I might not explain what I'm doing because I've done it so many times before, and I might not take into account a learner's perspective as much. So that's why I decided to do it with my children, so you can sort of see how they figure out how to do things and they improve their lab skills. Ideally, we'll be coming back later and doing some labs in person. I'm not sure if we'll do this one, but if we do labs in person, of course, you have to pay attention to all the safety factors that are involved. So please pay attention to that. Remember that density is mass divided by volume. So what you really have to measure is the mass, and what you really have to measure is the volume. You need those two things, and then, of course, it comes down to calculating, just dividing the mass by the volume. We often measure mass on a balance. You'll see that. There's many different kinds of balances. There's electronic balances that are quick and easy. There's triple beam balances that are nearly as accurate. And then there's taking the mass of one object against the other, the double pan balance, and you'll see all of those in this lab. For volume, of course, ideally, you just use a graduated cylinder or even a beaker if it's too much for a graduated cylinder. And the great thing about those is they have markings on them. The markings tell you what the volume is. You just read it off. As long as you read it eye level very carefully, you can get a very good volume of a liquid. The tricky thing about measuring liquids, though, is making sure that it's on a flat surface, looking at eye level, and reading the bottom of the meniscus. The word meniscus is an ancient word that actually means crescent moon, okay, because of the shape. Look at the top of that water. See how it's curved like a little crescent moon, like a thin moon that's just appearing after the new moon. And it turns out that a lot of what you're seeing there is magnification by the glass around the sides, making it look like a lot of the water is above that. But in fact, it isn't. Very, very little is, almost none. So we always measure from the dead bottom of the meniscus to get the best volume measurements. And then, of course, what about water? Well, remember the definition of the gram? This is one reason why I wanted you to watch the notes on the metric system. The gram was actually created by filling a milliliter with water. So then what must the density of water be? Well, density is mass over volume, and if you have 1.0 gram, 1 gram, in 1.0 milliliters, 1 milliliter, what would you get when you divide those? 1.0, of course. And then the units, grams per milliliter, that is the density of water. So if you want to know if something is going to float, just compare it to the density of water. If it has a lower number, lower density than water, if it's rarer than water, then it'll float. If the density is higher, if it's denser than water, it will sink. Well, not all liquids have the density of water. And of course, you could also write that as 1.0 gram per cubic centimeter. We don't usually do that with liquids. We prefer to write them in milliliters, but just so you realize that is the same thing. So the density of water, you could say, is 1.0 grams per milliliter or 1.0 grams per cubic centimeter. One thing we do in this lab is make a column of liquids. So why does this work? This works partially because different liquids have different densities. So if you pour them in very carefully and try not to disturb them, try not to agitate them by pouring in too quickly, you can keep them separated by their density. So which one would go on the bottom? Think about it. Just like the shot put would sink in water, if a liquid had a higher density than water, it would sink to the bottom. So that's the one we put in first. And if a liquid has a lower density than water, if it's rarer than water, well then we put it in after the water, we put them in order. So notice when we get to that part, think about, did we do it in the right order? Are they in the right order, and why does that work? There's a few other issues that come into play here, honestly. We'll learn about later, like polarity is a factor here, but it doesn't change the order, the sequence of them, okay? And we are going to be dealing with some objects that are not strictly rectangular prisms. We are going to have some that are triangular blocks or prisms. But look at those two triangular blocks, put them together, and isn't that whole thing just a rectangular prism? So isn't it really just width times length times height? If I were to pick, let's say, that bottom left corner. By the way, the trick of picking a corner only actually works perfectly if you pick a corner that has all right angles. I did not mention that earlier. So see that lower left-hand corner? I'd probably pick that corner. Or the top right corner? I'd probably pick that corner. But it's a triangle, so what if I just have one of those? Well, what would I do? I would divide by 2. I would measure the 3 dimensions, multiply them together, and then divide by 2. I would not try to measure the base times height, because measuring height of a triangle is less accurate than measuring its edges. So if you try to measure the height, you might not be getting it right. Okay, so I would prefer if you use the 3, just like we did for the rectangular prism, the 3 that meet at the right angle corner, and then divide by 2. It works perfectly that way. Then the last part of this lab will be using aluminum foil. Okay, by the way, I'm throwing in notes for the lab into these notes so I don't have to do a separate one. Okay, so you can refer back if there's any confusion. Well, aluminum foil doesn't appear to have a third dimension. I can see it has 2 dimensions there. It sort of has width and length, but it doesn't seem to have any height. But it does. It's just the height is very, very tiny, almost microscopic. I mean, we can see it, but it's hard to measure it. So it's not actually microscopic, but it's very, very thin. But still, just like any object, aluminum foil does have density, and density equals mass divided by volume. Now, in the aluminum foil calculation, you are actually given the density. So we actually have to rearrange this equation. So I'm going to do a little mumbo jumbo here, a little mathematical trickery. As you know, well, let's replace them with letters. D equals m over v. And as you may well know, if there's no denominator, well, then the denominator is 1. Now, if you want to solve for volume instead of density, if you know the density, well, there's a little trick you can do. I don't know if you're aware that you can always do this. If you have one of these proportions set up with an equal sign in between, you can feel free to switch those around. The other way to do that would be to divide both sides by d, multiply both sides by v. That would be doing it in 2 steps. That's another little mathematical trick. And then the problem is that we don't really measure the volume of the aluminum foil. We measure its width and its length. So we want to split up the volume into width times length times height. And we can measure the width and the length, so we want to get them on the other side. So if we divide both sides by width and length, we wind up with this. And now we can just get rid of that one denominator because it doesn't change things. And this is actually the equation that we're going to use to solve for the height or the thickness of the aluminum foil. Remember, the thickness is one of the 3 dimensions. We just can't easily measure it, but we can easily calculate it as long as we know the mass, as long as we know the width and the length, and the density. The density, of course, is given to you on the lab. So that's probably the trickiest part, and just do a good job, and you know it's got to be a small number. Take a look if you have aluminum foil at your house. Take a look at it. If you have a ruler, hold it up to it. You can sort of see that it's going to be a pretty small number. It's not going to be like a centimeter thick. It's going to be a very tiny number. So don't be surprised when that is a small number answer, and make sure to give it a unit. So this equation you will use to calculate the thickness of aluminum foil. The thickness, by the way, is the h. It is the height. And then for our labs, what we often do, what we almost always do, is a lab report, just to make sure that you think about what you've done. In this case, what you see on the video. So even though it says you, this is the lab report we use when you actually do it. Well, you might have, it's going to be my kids doing it, but you're going to sort of describe as if it was you. Try to imagine that you performed this lab. And so when it says describe how you measured the density for liquids, just like what was measured, all right? And notice that it's different for solids. There's some complications measuring the density for a liquid, and there's different complications measuring the density of a solid. Think about what those are. And then the column of liquids was what I just showed earlier with the several different colored liquids in that cylinder. So describe how that works. Use the word homogeneous or heterogeneous. Homogeneous, by the way, means that things are very, very well mixed. They're all mixed together kind of evenly. So they would all be like one big layer, one big color. Heterogeneous would mean that they're not. Heterogeneous you would think of as a bad mixture, where you see layers of things. So it's pretty obvious which one we're going to have for the column of liquids. And then think about, what does density really tell you about something? Okay, what is it in reference to? I mentioned that just earlier. Like, think about what has a density of 1. That's what it's in reference to. And then describe how you found the thickness of the aluminum foil. Okay, describe how we pulled the height out of the formula for density. Try to give me some sort of explanation, kind of like the mathematical trickery I was doing a little earlier. So a lab report is done in addition to the lab. It is submitted with the lab. So please make sure that when you do our first lab, you do the lab report as well. It is part of the lab. It's not a separate assignment. Make sure, and that counts as part of the score on the lab. So just make sure to do a reasonably good job. A lab report should be answered in sentences. There's got to be at least a sentence for each of these items. You can write more than that. You can write about other things you observed in the lab, or if you think there was lab error that was made, you can describe that. Try not to be too critical. You know, they did their best. And that is part of a lab. So please do a good job on our first lab, and we're going to have quite a few of these. So that is the end of the notes on density. We are now getting into, this is a major concept in chemistry.